So what I'm going to talk about today is reference frame independent quantum interpretation. So the idea is that the state of your quantum system, although you might not know it, is always defined, is always described with reference to some reference frame. For instance, if you're thinking about a spin-half particle, you want to talk about the angular momentum eigenstates, you need to say with respect to what axis. And if you change the axis that you're talking about, the state of your system, the description of the state of your system, will change. So in teleportation, a hidden assumption is that the two parties share a reference frame. But this is often not the case. And so what I'm going to give is a way of constructing protocols that work despite the fact that the two parties' reference frames aren't aligned. So it's possible. It's sometimes possible. The way it works is it requires communication of unspeakable information. What that means will become clear quite briefly, but basically what it means is that the classical channel we use has to be correlated in some way with the particular type of reference frame that is relevant to the system. It's good because there's no transfer of information about the reference frame configuration, and it doesn't require any prior communication or additional resources. It uses just the same thing as a normal teleportation protocol, an entangled state in classical communication. And it depends on, so whether you can do it or not, that depends on so the formalism for reference frames, where you have a group of reference frame transformations, and that has an action on your system, which describes how a change in reference frame configuration affects your description of states and of operations. So whether you can perform this reference frame independent interpretation depends on the action of the group of reference frame transformations on the system. But the key restriction is the group must be finite. And I'm going to provide some constructions of these protocols and some results regarding existence. So how it fits into previous work. Well, this hidden assumption was first noted in a paper by Van Enck from 2001. But since then, it's been shown that if a group of reference transformations is infinite, basically, if it contains U1, then perfect teleportation is impossible if reference frame, for all kind of relative reference frame alignments. But this theorem doesn't apply to finite groups. So since then, we work on imperfect protocols on the infinite case that work with some probability of success. But we're going to deal with the case of a finite group. And so applications of this result, there's an application, the obvious application is if two parties have systems defined according to reference frames, and they don't know each other's reference frame configurations, and they have no way of communicating their configurations to each other, then they can still perform teleportation. That's the obvious use. And it works even with dynamic frame alignments. So even if the frame alignments are shifting constantly throughout the performance of the protocol, it will still work. Then the other interesting application is for reference frame hiding. So I have a cryptographic application. So it was noted in this paper from 2004 that in a super selected world, certain things are cryptographically possible and impossible that aren't normally. So, and one way to induce a super selection restriction is with reference frame uncertainty. So, the great thing about this is you don't change any reference frame information. So you retain a super selection restriction and still be able to perform teleportation. And many of the reference frames that crop up in applications are infinite. Well, how does it affect that case? Well, you could perhaps discretize or kind of probabilistically discretize the group of reference frame transformations using limits of prior communication or some other method, and then you could use our protocol. Or there's another interesting possibility, which is that you could take imperfect protocols as limits of our perfect finite group schemes. So those are the applications. And another more general application is that this is kind of a general framework. It demonstrates that CQM, which is how these results were found, is a good way to work with reference frames in quantum information. So we've already had the introduction. So first I'm just going to explain the formalism of those reference frames and how they relate to group actions. Then I'm going to demonstrate our protocol by example, then talk about existence and construction, and then finally give a kind of categorical perspective on the whole thing. So reference frames are implicit in the description of quantum states. So here are some examples. I've already talked about the spin-half particle, but for instance with photon number, if you have like photon number 0 and 1, those have different energy eigenvalues, so the relative phase between them changes gradually. So if you want to choose your basis states, you need to kind of pick a 0 at a time. So there's a reference frame, it's kind of a time reference frame in there. And a finite example, if you've got a particle in a cuboidal box, then the ground states will break the symmetry of the box. So in order to differentiate the ground states, you have to decide which way around is you have to be able to differentiate the sides of the box. So that's another reference frame there. But in all these cases, they have an associated group of reference frame transformations. So for the angular momentum, I mean that's going to be a group of rotations, three-dimensional rotations. So that's SO3, or at least some kind of subgroup of it. For the eigenstates of the photon number, well, time evolution is periodic, so the group is U1. And for the particle in the cuboidal box, that's the orientation preserving rotations of the box. So that would be the symmetric group S4. Okay, so this is the formalism. This is the key bit. So in the Hilbert space is going to carry a unitary representation of the group of reference frame transformations that tells you how your reference frame is going to, how a change in reference frame is going to change your description of states and operations. It's very simple. If the reference frame configuration transforms by some element within the group, your state will be described as psi in your old frame, and it will just be acted on in your new frame. And your linear map would be L in your old frame, and its conjugation acted in your new frame. So that's just the way it works. Okay, so now I can talk about teleportation protocols. So this is just you can classify them basically. I want to say this first. So if your Hilbert spaces have minimal dimension, so every Hilbert space has the same dimension as Alice's Hilbert space, then teleportation protocols correspond to UEBs as follows. This is your shared entangled state. Alice measures in this basis here, and Bob's unitary correction is this thing here. Unitary error base. This is just a basis of the endomorphism space, so that all the elements are unitary and they're all orthonormal. So that's just something. But okay. So this is the key bit. This is, if you understand this, this is the whole idea. So I mean the next 4 slides essentially it's all in here. So here's the situation. Alice and Bob are in labs with different orientations in space. So the orientations are related by some kind of element of the rotation group, and they share this entangled state here. There's going to exist some finite subgroup of this rotation group, and they know that the change in orientation is within this subgroup, and they know its action on the system, and they want to perform teleportation of a quantum state without revealing their orientation. So how are they going to do that? That's the question. So let's try it in the normal way. So let's say that the action is this. We'll show in a bit that the actual matrix element doesn't actually matter. The only thing that matters is the isomorphism class of the representation. But let's suppose it's this. This is the valid action. It's unitary. It squares to the identity. And okay, this is a UEB here. So I've chosen this UEB specially so that it works. So this is the type of UEB we need. But this is okay. So this is the action. This is the UEB. Great. So they can use this to perform teleportation normally. Let's do a normal teleportation protocol and see what happens. Suppose Alice communicates the measurement result to Bob in a normal way using just bits. She just phones him up or something and tells him what happened. There's 2 cases. If Bob's reference frame is correctly aligned, I mean we've got it could be up or it could be up down. So if Bob's reference frame is correctly aligned, the procedure will be successful. Sorry, I should have said we've assumed that the subgroup is Z2. This is the simplest case. We've assumed that the subgroup is Z2. So that means there's 2 reference frame configurations, up or down. And the change in reference frame configuration from up to down and from down to up acts like this. Right, so suppose she communicates it normally. There's 2 cases. If Bob's reference frame is correctly aligned, it'll work. I mean, it just would. If Bob's reference frame is upside down, then it's going to fail. And so why is it going to fail? From Alice's perspective, Bob's correction was wrong. So she communicated the right measurement result. She gave him the right answer, but he performed the wrong unitary. From Bob's perspective, Alice gave him the measurement result I. He performed the correction UI, but the thing she communicated didn't correspond to the actual state she measured. And in fact, you can prove a theorem about this. If she sends it in a normal way, the procedure only works for every reference frame alignment when G acts by a global phase. So when G acts trivially. And I'm going to skip over the proof. That's kind of okay. So we're now going to present a solution. So rather than communicate the measurement result in bits, she's instead going to send 2 arrows to Bob, physical arrows, pointing up or down. So what's she going to do? Say her reference frame direction is up. If she wants to communicate, she uses this encoding So if she wants to communicate to 0, she sends up, up. If she wants to communicate to 1, she sends down, down. If she wants up, 2 is up, down, 3 is down, down, up. So Bob knows the encoding and then infers the measurement result, assuming that his reference direction is the same as Alice's. I suppose it's aligned upside down with respect to Alice's, then you can see that 0, 1, 2, or 3 it commutes 0 and 1 and 2 and 3. So let's remember that they get switched. But now, the UEB is such that the communication error is going to cancel with his correction error. So Alice sent 0, Bob received 1, he performs his correction U1, but in Alice's frame, but what he's actually doing is performing U0. So Alice's communication error cancels with Bob's correction error. So this permutes 0 and 1, this permutes 1 and 0, and this permutes 2 and 3. So the UEB works regardless of the reference frame alignment. It works regardless of reference frame alignment. So you have a successful reference frame independent teleportation there. So if we look at this, there's two crucial elements. Firstly is the fact that the reference frame was permuted under the conjugation action of G, and we call such a UEB G equivariant. And secondly, the classical channel carried a G action. So Bob's reference frame alignment actually affected his perception of what was going through the classical channel. And we made the measurement results guide inverse permutation to the UEB. So if we can find a suitable classical channel, we say that this communicates unspeakable information in this classical channel. If we can find a suitable classical channel and a G equivalent UEB, we have a reference frame independent teleportation protocol. So now I'm going to discuss how we can find those two things. The classical channel is nice, it always exists. So so if you have a G equivalent UEB, then you can always find a suitable classical channel. How do you do that? Well, Alice decoheres in the bases corresponding to the UEB. Her system is now in a classical state. She now sends the decohered system itself to Bob. Bob then measures the system, performs the correction corresponding to his own measurement, but he measured the system himself, so there's no problem. And this procedure is reference frame independent exactly when the UEB is G equivariant. The reason being that if the UEB is G equivariant, the basis Alice decoheres in will be the same as Bob's measurement basis. So it just permutes the measurement outcome. So if it wasn't G equivariant, she might decohere in some basis, and then it would arrive to Bob, and Bob would measure it in a different basis. But the G equivariant condition makes this reference frame independent. But it might be more practical to use an alternative classical channel. And you can do this. So the arrows channel can be generated to any finite subgroup. So rather than Z2, if it was Z4, so like this, Alice could just send an arrow pointing up, left, right, down. And you can generalize that to any finite subgroup, yeah. But what about a time reference frame? It works for time as well, so you can come up with a time encoding. So suppose we've got some kind of finite group of time translations. Then signals sent by Alice, which arrive at some time, arrive at a different time, so she can encode her measurement results in the time of arrival of signals. And using that, she can get the inverse permutation to the G equivalent UEB. So that's great. Now, the other thing is finding G equivalent UEBs. Obviously, there are more classical channels than this, there are more situations than this, but the experimentalist, I suppose, would need to come up with a good classical channel. Okay, so now, finding G equivalent UEBs. So this is the other half, and this isn't so easy. So, we can't hope for a classification of G equivalent UEBs, really, because you don't even know, there's not even a classification of UEBs when the G action is trivial. So that would be too much to hope for. But what we can do is we can show non-existence, and we can also provide some methods for constructing them. And this is sort of a mathematically interesting problem. The way we do this is we use G equivariant orthonormal bases. These are easier to classify. You have a G action on a space, and then you have an orthonormal basis of the space whose elements are permuted by the action of G. So you just call that a G equivalent orthonormal basis. And obviously, every G equivalent UEB is a G equivalent orthonormal basis itself of the endomorphism space of H. And you can easily classify these things. So here, I'll just quickly run through it. So you've got G set, the category of sets and equivariant functions. And there's an obvious functor from that to that G. So if you have a G set, you can just take the G set to the free Hilbert space on its elements, extend the G action linearly. And so if you think about it for a little while, you can see that the G-equivariant orthonormal bases, they can only exist in representations in the image of this functor. But this category G set is quite easy to understand, because every G set is a disjoint union of coset spaces, so you can decompose G sets as coset spaces. And two coset spaces are isomorphic if and only if they correspond to conjugate subgroups. So the simple objects of this category G set are just the coset spaces. And they each correspond to conjugate subgroups. And this is an additive functor, so disjoint union goes to direct sum. So in order to classify the objects in the image, all you need to do is find the images of the coset spaces, and then the things in the image will just be those direct sum. And using something like this, you can easily show there's no G-equivalent UEB for this representation of S3. So you just decompose V tensor V star as you just find it what it is as a character. You find the characters of the basic permutation representations, and you show that you can't decompose this as a sum of them. So sometimes they don't exist. But this doesn't work for all irreps. So you might think that oh, it's because it's irreducible. You can't do it for reducible representations. But the 2D irrep of D8, for instance, the endomorphism space of that representation decomposes as basic permutation representations. So, okay, so they don't always exist, but when they do, how do you construct them? So we've got a sufficient condition here. So what you need is you need to find a G-equivariant orthonormal basis of the vector space, and then you express the elements of the elements of G in that basis. So they're going to be, the representation is going to produce a homomorphism from the elements of G to matrices, obviously. In this basis, because it's a G-equivariant basis, those matrices will be permutation matrices. So if you can find a Hadamard matrix that commutes with all those permutation matrices, then you can use this information to construct a G-equivariant UEB. This is the G-equivariant UEB if you let VI be the elements of the basis and H be the Hadamard matrix. This is the Jth row of the Hadamard matrix, expressed as a diagonal. This looks complicated, but the way it was found, the way I realised it was G-equivariant, is because it's a categorical construction. So categorical constructions go through, and lots of UEB constructions are categorical, so they can all be used. They'll all work. This was a categorical construction. Okay, so this is a nice sufficient condition also that we've found. So suppose we've got a G-equivariant orthonormal basis, and the dimension of the Hilbert space is less than 5. Then regardless of G, it doesn't matter what the G action is, you can always find a G-equivariant UEB on this Hilbert space. So in dimensions 1 and 2 it's obvious, but 3 and 4, by the last theorem, we need a Hadamard matrix that commutes with all the elements of G when you express them in that orthonormal basis. Okay, so that image of G in the matrices is going to be a subgroup of the permutation matrices. So the worst case is that it's all the permutation matrices. So you want to find a Hadamard matrix commuting with all the permutation matrices. It's quite a simple-minded sort of proof, really. And then you find what the matrices that commute with all the permutation matrices look like. They're quite easy to understand. They just have identical entries on the diagonal and then identical entries everywhere else. So there's two parameters basically. And then you find out what it takes for such a matrix to be unitary. That's equivalent to these two equations here. And these equations can be satisfied. So you want it to be a Hadamard matrix, not just a normal unitary matrix. So these equations can be satisfied for the modulo equals modulo 1 over D, if and only if D is less than 5. So that's how this dimension less than 5 result comes about. But it's a nice sufficient condition for small Hilbert spaces. So there you go. Those are the construction results, existence results, construction results for the G-equivariant unitary bases. You can always find a classical channel. So what does this have to do with CQM? So in CQM, one of the ideas of CQM is to talk about quantum information structures and concepts in terms of their algebraic structure as algebraic objects. And this is quite successful. I mean, so classical structures, that's an algebraic structure. If you put it in F-Hilb, you get orthonormal bases. And so you can think about doing the same thing for quantum teleportation procedures. So the quantum teleportation procedure is certainly an orthonormal basis, so it's certainly a classical structure. But it's a certain kind of classical structure that satisfies this equation here. So what do these correspond to? In F-Hilb, they're exactly the unigeo bases. They're exactly teleportation. In Vel, they correspond to one-time pads. but in vet G, this category with, sorry, Mr. J there, in vet G, which has objects, unitary representations, and morphisms intertwiners being sort of equivariant maps, that's the kind of obvious category to do reference frame dependent sort of quantum mechanics in. In vet G, they correspond exactly to the G equivariant unitary error basis. So in all these categories, they represent teleportation. And the other nice thing about categorical quantum mechanics is if you can find a categorical construction of these things in F Hill, then those categorical constructions usually carry over to vet G. So you can take things from F Hill, put it in vet G, and you get kind of the G equivariant equivalent. So this is probably a very useful way of talking about reference frame sort of dependent quantum mechanics, reference frame dependent quantum information too. And also, I mean, it's unclear how to generalize sort of non-categorical constructions of UVs to the G equivariant set. I suppose it's just a reinforcement of the Great, so ideas for future work. So the mathematical problems of I mean, obviously these G equivariant UV results of constructing them aren't the best you can get. You must be able to do better. Mathematically, it's quite interesting. So you want to find kind of, you've got some kind of subgroup of the unitary matrices, and you want to find a particular type of UEV commuting with these things. So it's an interesting mathematical question. That's something to look into further. The other thing is applications to cryptography. So I think this might be kind of an interesting use of this finite group result. Using the kind of super selection idea of Kitaev, but also if you think about multi-party sort of secure multi-party computation, or something like this, well, if the parties have misaligned reference frames, then they can't communicate their state to each other unless they can communicate unspeakable information. So you have some sort of built-in security there, and then, but they can perform a universal computational primitive, which is teleportation. So this is it's interesting to think about this. Another thing is the infinite limits of reference frame kind of protocols, which I talked about earlier, kind of building imperfect infinite protocols for more general cases using these finite protocols. And the other thing is, so you following this categorical thing further, so what we did here, we put a teleportation protocol in vet G, but there's certain categories that that describe kind of the theory of anyons, the theory of anyons. And what's a teleportation protocol in one of these categories? There are certain very simple categories like quantum doubles of finite groups that you could look in. You could look these protocols in. They're very well understood. They're very well described, and there might be some interesting sort of physics that could come out of that. So thanks for listening.
Any questions, comments? Alex?
Could you go back to this picture of characterizing teleportation? Can you give some interpretation of what's going on?
Right, sure, yes I can. Okay, so there's two explanations of this. The first, so here we've got the vector space. Here we've got V, and here we've got V dual. So this is an orthonormal, and classical structure is an orthonormal basis. So this is an orthonormal basis on the endomorphism space of the Hilbert space. This condition here, mathematically, it corresponds exactly to the elements being unitary and orthonormal. But from an operational perspective, I mean, you can sort of see this as Alice has something. She shares this entangled state here. Then she measures. So she copies in a classical structure. So this is going to be, if you traced out this here, that would be a mixed state. That would be the mixed state in the basis she's measured in. She then communicates one bit of, you forget about this. She communicates this to Bob. Bob does something. This obviously has no operational interpretation, but he does something. And that's the same as random information was generated here, and then this went from Alice to Bob there. So it has this kind of operational interpretation, but this has to be, you have to think carefully about what this is.
Yes, go.
Could you comment on the relation of your work with the approach where people use like decoherent free subspaces when you think of the tensor product representation, and the multiplicity space as the space where you encode the information? I mean, you can do quantum information without the shared reference frame, by considering?
You can, yes. So this doesn't fall under our framework because this would require a larger Hilbert space in which you can encode the information. So this, you could actually use the same CQM approach in the category representations. That works fine. And the decoherence-free subspace, basically, it comes down to the identity subspace of the representation. You can encode things in that. But this thing here the idea is it uses exactly the same resources as a normal teleportation protocol. You don't need bigger Hilbert spaces, you don't need encodings or anything. It just works normally. I think the key thing here is the use of unspeakable information to communicate with someone. I think that's the kind of key new idea of this work.
Stefano?
Hector, I guess. Maybe you first.
Who?
Hector,
Oh, okay, yeah, I can't see because you're in my back. Okay.
Do we have any? Do we have any nice results about the group theoretic properties? Is it easy for abelian groups if we can factorize the groups? Can we factorize the algorithm?
So if you had finding the geoequivalent UEVs for particular types of groups, certain groups would certainly be easier than others. The representations of abelian groups are very easy because they're all sums of one-dimensional representations. So there might be some nice results to be found for abelian groups and for certain subclasses of groups, but I haven't found them yet. It's work to be done.
Yeah, so you work with the category of G-representations, which suggests that, and you construct G-equivariant orthonormal basis in the process, which suggests that you might, from a F-field perspective, be working with strongly complementary bases. That's what G-equivariant orthonormal bases are for a finite abelian, at least group G, or even non-abelian. So the question is, have you thought about the relation with strongly complementary observables? Because usually one in teleportation has complementary ones, and then one thinks maybe strongly complementary ones are not really needed. But in this approach, it seems pretty clear that strongly complementary has something to do with G equivariance and additional structure, maybe it's reference rate.
I hadn't thought about that, but it's a very good point. Yeah, I will think about it. Yes.
Just rep G is basically the Allenberg-Moore category for the monad induced by the monoid of by algebra pair. So
Right.
ultimately, that's another way perhaps to look at that.
Ross? I have the same question.
Okay.
So anything else? No? Okay, we thank Dominic again.